Hi, I'm Hannes,
Hello, I'm Dominic.
and today we have Equivariant Subgraph Aggregation networks presented by the three main authors. And if you want to join our reading group sessions yourselves, you find the link in the description.
Thank you very much, Hannes. So I will start. So just a small disclaimer, we will alternate a lot during the presentation, so it's going to be a bit dynamic. So Beatrice and Derek will chip in at some point, and we'll do this again and again. So just a disclaimer. Right, and yes, this project, as you were mentioning, sparked directly from the 2021 Bagamal Summer School. So maybe before starting, a huge thanks to the organizing committee, Guada, Mehdi, Tim King, Daniel Platt. I'm forgetting someone, but the organizing committee, yes. Agai Maron, by the way, was the tutor for this project, and then we decided to bring this project to continue working on this project basically after the summer school. And yeah, so let's get started. Okay, right, so let's start with some motivation, and then we'll go through our method, and then we'll analyze it and discuss about experience and yeah, and this kind of things. Right, so let's start with maybe the very basic idea that was behind this whole project. So the idea was to define a new family of provably powerful graph neural networks, treating a graph as a set of subgraphs. So this is really the key concept. And then the idea is to process this set of subgraphs in a principal manner, respecting the symmetry of this new object that characterizes this new object. This is what we want to do and what we actually achieved to do to some extent. And yeah, now that we will unpack these aspects step by step in the rest of the presentation. Okay, so I think we can go quickly here because I believe this audience is quite familiar with GNNs, but yeah, in general, we can say that they are parameterized functions working on graphs. And one of the most popular architectures is probably the MPNN one. So it's the one where we update node representations, exchanging messages across edges. So we have messages that are aggregated in a permutation invariant function locally, and then this overall message from the neighborhood is used in conjunction to the current representation to update the representation of a node in particular. And in this original formulation, it's important to notice that MPNNs, but generally, let's say, standard GNNs are permutation equivariant. And this is something that we will get to back later. Okay, so what's the problem with GNNs? Well, we are all very aware of this. So the problem is that no matter how we choose to disaggregate and combine functions, they are bounded in expressive power. So at most, what we can hope for is to get the same expressive power of the 1WL test. This is a result that has been shown introduced and shown in the Gene paper, also in a paper by Morris. I think it was concurrent. And the problem with this is that very simple graphs, such as, for example, the pair that we're showing in the slide, they cannot be distinguished. So MPNNs actually will assign them the same representation no matter what. Okay, next slide, please. Yes, so what's maybe a few words about the WL test, which might be useful later. So what's the WL test? So it's a polynomially fast heuristic to disambiguate non-isomorphic graphs, and it iterates color refinements. So we start by coloring nodes with a certain color. It's constant if we don't have initial labels on nodes, and then we keep iterating this update rule the idea is we injectively hash the current color for a node along with the multiset of colors from neighbors according to the graph connectivity. And we keep doing this, and we can, in this way, basically represent a graph as a color histogram. So we can basically gather the colors from the nodes and then define an histogram. And the concept behind the isomorphism testing with this procedure is that whenever the histograms of two graphs diverge, then we can conclude that the two graphs are non-isomorphic. The problem with this is that it's only a sufficient condition. So this means that, well, if the histograms are distinct, then we can conclude the graphs are non-isomorphic. But if the histograms actually coincide, then basically in that case, we cannot actually conclude much about whether the graphs are isomorphic or not. And as we have already observed in the previous slide, we do have examples of graphs which are non-isomorphic, but they would in any case be assigned the same histogram. Okay, so why in general expressive power is important? For example, some molecular graphs cannot be distinguished by the 1WL test, and therefore not even by standard message passing neural networks. So it's not just about some exotic counterexample. So we have actually molecules, real-world molecules, which would be assigned the same representation by a message passing neural network. And this might be a problem if they, for example, are assigned different targets to be predicted, right? And second, another important point is that it has been shown that there is a link between isomorphism testing and counting of substructures on graphs. So an implication of this is that 1WL cannot count non-trivial patterns, for example, such as triangles. So in general, it cannot induce count patterns with 3 or more nodes. So yes, in this case, triangles and cycles, they cannot be counted. And well, there is actually evidence that these substructures might be correlated with some targets for example, cycles might be correlated to some property in molecules. So these limitations are directly inherited by MPNNs, as I was saying. So this is why, in the first place, we would like to design MPNNs to be more expressive than the 1WL test. Okay. There have been several attempts and somewhat diverse research directions have been followed, trying to, aiming at GNNs, which are more powerful than 1WL. So one idea is to mimic the KWL test in general, or the hierarchy. So the idea is that the 1WL test can be extended to higher order, higher dimensions, let's say, and in so doing, we can gain expressive power. And the idea is that we can form a hierarchy of tests with greater and greater expressive power. And KGNNs try to mimic this hierarchy. The problem with these models is that they fundamentally they are not local, which is a very nice property of standard GNNs, and they easily get computationally intractable. A somehow orthogonal research direction instead is it deals with augmenting nodes with random node features or identifiers. And in principle, we can gain expressive power at the point of having universal models. The problem is that we may lose permutation equivariance, which was one of the properties we highlighted before that is enjoyed by classical GNNs. And we may have problems in generalization outside the training set. So these are some drawbacks. And another direction, just to mention one more, it's about explicitly introducing information related to substructures. Since 1WL cannot count non-trivial substructures, then the idea would be either to inject this information as an exogenous features, or to kind of redefine message passing to work directly on substructures. The problem with this is that at the end of the day, when you want to solve a specific task, you would need some form of domain knowledge to design your filter bank. So to decide which are the substructures you would like to take a look at, and the ones for which you would like to do some preprocessing and then inject this form of information into the model. So to some extent, we are still, we still have to face some pre-engineering work. Go on, us.
In the paper, when you mentioned substructure aware message passing, so to say, then you mentioned the sentence, or you have the sentence. Both types of approaches require a pre-computation stage that, though reasonable in practice, might be expensive in the worst case. Like, is this actually the case that this can be expensive, like the CW networks, for example, the pre-processing? I mean, yeah, to me it's
so it really depends on the as I was saying, it really depends on the substructure bank, and not only that, but also the graph distribution you're working with. So in any case, if you need to match substructures onto graphs to do some form of reprocessing, so the worst case complexity is exponential in any case. Yeah. This is worst case, right? So in the case, for example, of CWN, what we showed is that if you, for example, care only about rings and rings on molecules, in practice, this is more than tractable, because rings are not so represented in molecules, so they will match in a sparse fashion. And in general, you could in principle also consider specialized algorithms to match them. But if you, for example, work on a task where you don't have any idea of what's the substructure that could be important, or maybe say that even if you know it, maybe say that the substructures are overrepresented, so maybe they occur exponentially in terms of their cardinality on graphs, then this could be a problem, of course, yes. So maybe, we can say that with this work, we also try to do target a more general application domain, like more general application domains. So we don't want to necessarily be too specific to some tasks, say molecular modeling or something like this. So in general, say that you have a new task you want to tackle. How can we the idea is we would like to get some more expressive power without requiring too much pre-engineering or too much domain knowledge. But at the same time, we would like to retain permutation equivariance. This is the idea. It sounds like you're not convinced.
Like, I mean, CW networks, for example, what is the situation in which it gets expensive? Like, of course, we can always have cook up some worst case, or but like, can we also cook up a real example, a real task where it would be very expensive?
So, for example, if you work with right. So, for example, if you work with proteins, protein association networks, right? So you may have that your graphs. So you may have that your edges are there, and then but they might not necessarily be of high confidence, because, for example, you have many measurements you can take to decide whether two proteins interact. And yeah, it's really like not, there's not really like a golden rule to say, well, these proteins are interacting or not. So you would deal with graphs which are very, very dense. And if you want to, for example, match clicks, you might get into trouble. So this is a problem, for example, if you really want a real use case.
Yeah, okay.
So in general, if you are able to work with substructures, but in general, subgraphs, this is like the subtle shift, if you want. So from substructures to somehow subgraphs. So if you work with subgraphs where they are generated by a policy, and this is still not exponential in the worst case, then you can still gain some expressive power and at the same time retain equivariance. Yeah. This would be an idea, but in general, you might not even know which substructures are important for your task, right?
Yeah, right. And there your point always holds that, yeah, these substructure choosing architectures, so to say, are not the best. because we have to know.
They work very, very well for some tasks.
Yeah.
Don't get me wrong. Also because I'm one of the main authors on many of them. But in molecules, I think they really shine, for example. But there might be something else, right?
Okay.
If Derek or Beatrice would like to chip in, I think.
Just on a purely theoretical level, there's very strong complexity lower bounds on the amount of time you need to count certain subgraphs. And it also tends to like intuitively scale really poorly as your graph gets denser. Molecules are really sparse, but even a bit denser could be hard. But yeah, that's just purely theoretically. Yeah. That's assuming you know the substructures you want to count.
Yeah, okay. But I was just, for example, thinking about the CW network. So we just have these rings. And,
yeah, rings are nicer. Yeah.
Okay, but then let's keep going.
Yeah, so I'll start talking about our method. So Fabrizio just went over a lot of negatives of other methods and things that the community is working on. So from these negatives, we can turn them into positives that we strive for. Like for instance, we want provable expressive power, greater than 1 WL power, that is. And you want to have not much engineering or like domain specific knowledge required. Of course, you also want these to be computationally tractable, especially for sparse graphs, because pretty much most graphs that we deal with are very sparse. And we still want these to be equivariant to permutations on nodes. So like to make a method that achieves these goals, we build off the following intuition, which is even if two graphs are hard to distinguish or it can't be distinguished by 1 WL or message passing, they may contain subgraphs which instead we could easily separate with message passing. For instance, these two graphs, as Fabrizio said earlier, they're equivalent under message passing. But if you just delete one edge from each of these graphs, then it can be easily seen that message passing will distinguish these graphs. So using that intuition, we build this framework called Equivariant Subgraph Aggregation Networks, which we abbreviate as ESAN. And the recipe is as follows. We take a graph, right? And then we map it into a set of subgraphs, which we call a bag of subgraphs, like analogously to a bag of words, right? And we do this via a function that we call the selection policy. So G maps it as a set of subgraphs. And then we process this bag of subgraphs in a principled way, and meaning that we will respect the inherent symmetries of this whole object, this set of subgraphs, in the architecture that we build. And we'll go over what these symmetries mean on the next two slides. So the policies that we choose, you could choose very many policies, but we focus on 3 really. So one of them is node deletion, which is in this first row, like you take a graph and then you make a bag consisting of all of its subgraphs that you obtain from deleting one node. Like this one, you delete the top node, this one, you delete the left node, and so on. Also, we do edge deletion, which is you take the bag of subgraphs where you delete one edge from each. You deleted this edge here, this vertical edge here, this edge here. And yeah, notice that the bags are of different sizes. This first policy is the bag is the size of the number of nodes. The second policy, it's the number of edges, right? We also consider ego nets, which is you map a graph to like all ego nets of each node on some depth, meaning you take all like the neighborhoods of each node and you process that. So like about these symmetries, mathematically, how we capture this is through this concept of equivariance. So if we have like a base space, a domain RD1 and a a target space RB2, and let's say H is a symmetry group acting on these two spaces. We say that a function f is invariant if applying a symmetry, like a symmetric element, has the same function value to the original element. And we say it's equivariant if this symmetry commutes with the function f. And in convolutions, like for instance, for translation equivariance, you could think of either 1D or 2D convolutions. Convolution commutes with translation, right? If you translate a signal and then apply the function, apply convolution, it's the same as applying convolution and translating. And the standard symmetry in graphs, which as we said earlier, graph neural networks are equivariant to. It is this, the symmetry is given by permuting node names, basically. So the SN is the group of permutations on n elements. It acts on a graph G by renaming node I to sigma I, or sigma I is like the new name of node I. And it acts on this adjacency matrix by swapping rows and columns. It acts on the node feature matrix by swapping rows, right? So in our case, when we have a bag of subgraphs, we want equivariance to this particular group SM cross SN, where M is the number of graphs, subgraphs in the set, and N is the number of nodes in each graph. So these are like pairs. The elements of this group are pairs of tau and sigma. So this action by sigma is permuting nodes in each subgraph in orange. This is the standard symmetry that we want graph neural networks to be equivariant to. But we also have this new element of our group, tau, which permutes graphs in the set of subgraphs, right? The bag of subgraphs, meaning we shouldn't care about what order the subgraphs in our bags of subgraphs are in, right? So this is like the kind of equivariance that deep sets is equivariant to. And a very important idea here is node alignment. So this is so basically, because we are making our subgraphs from one starting graph, this original graph, we want node I in each subgraph to correspond to node I in the original graph. So if you see these like yellow lines here in the middle figure, it's just saying that this node in this subgraph is like the same name as node 1 in the other subgraph, right? Node 2 in each subgraph is like, there's some identification there. And thus, what this means like algebraically is that the sigma in Sn that acts on graphs, subgraphs, is the same across all subgraphs. So when you rename nodes, you're renaming nodes in the same way in each subgraph. And we'll talk about this more in later slides. So to capture this equivariance in a neural model, we define two models. First one is DSGNN, which stands for deep sets GNN. And it's basically this, it uses this concept of like Siamese networks, basically. So you apply the same message passing neural network to each subgraph, A1, X1, all the way to AM, XM. And then you apply a deep sets to compress this whole set of graph representations into one representation. But we also have a DSS GNN, where we define layers in which you have one message passing neural network acting on a subgraph I to make, this is for computing the representation of subgraph I. But you also have another message passing neural network acting on this pooling of all subgraphs, right? So summing AJ across all subgraphs, summing XJ across all subgraphs. And one very important thing to note is that, well, first, deep sets GNN is just DSS GNN, where we don't have MPNN2. And yeah, maybe I'll take a question now before I go into the main idea. Dominique?
Yeah, I have a few questions here. So how many transformations you do? Because like in the previous example that you showed, with a very simple graph, you have like 4 different node dropping and like 5 or 6 different edge dropping. So here, do you apply a random number of these transformation before you do that, or like how many transformation do you use?
Oh yeah, so here we're just defining the deterministic, like full version of our model. So in the case of node dropping, this M is equal to the number of nodes. So we have number of nodes subgraphs. Later, we also have sampling methods, but I think, so actually this deterministic version turns out to be pretty tractable and efficient. We run it on basically every data set as well. Does that answer it?
So suppose you have like 100 nodes, then you duplicate the graph 100 times.
Yes.
And you say that this is scalable with large graphs? Like how?
It's scalable for the graph prediction tasks that we do.
Okay.
Like in practice, this turns out to just be like tensor operations, which is nice on GPU.
So you don't experience slowdown regarding that?
We experience about like 2 to 3 times slowdown compared to just a message passing neural network. We have some tables for the run times later, which is nice.
Okay.
But yeah, it's definitely some overhead, of course.
Okay. And have you thought about using like a random, like randomly dropping, let's say 20% of the nodes or 20% of the edges, like it was proposed in the drop edge paper, I think. So do you think that it would work as well if you did that instead? Because I think you still preserve most of the expressive power, but you avoid the increase in computation.
Yeah, it was also proposed recently in drop GNN, where they drop nodes explicitly. And yeah, we somewhat do this in that we have subgraph sampling. So we don't drop like 20% of nodes in one graph. What we do is we take 20% of node deleted subgraphs, right? And what this means is like we take 20% of nodes, delete each of those single nodes and add that to our bag, if you see the difference, right?
That's what I meant.
Actually. Oh, okay, yeah.
To not take all of the possibilities, but take
20%. Precisely. Yeah, and yeah, we're gonna go over that later in the experiments as well, and it turns out to work out pretty well for us in runtime and accuracy. Yeah, and yeah, Hannes?
Yeah, so I just wanted to replay how you explained DSS-GNN and hope that you don't tell me that I got something wrong. Yeah, so we go ahead and have the bunch of different adjacency matrices. Like now I'm just looking at my ith graph and I want to get my new X or my new representation for the ith graph after applying this new message passing layer you have here. And this layer takes as input my own adjacency matrix, so the AI, and I also take the adjacency matrices of all other subgraphs. So where you maybe deleted a bunch of nodes or a bunch of edges, and then you sum all of these adjacency matrices of all of the other subgraphs. Like we really just end up with an adjacency matrix that has where maybe we removed some edges, and now these edges, for example, can also come back because we're adding adjacency matrices where they still included the edges, and then you're using those or this new adjacency matrix for another message passing neural network, and then you sum up the representations and end up with our layer output.
Yes.
Nice.
Yes. And yeah, so in particular, this pooled adjacency, the sum of the adjacencies of subgraphs, you use that for like your graph convolution. Yeah.
Yeah, and the sum of the adjacency matrices is like What happens if I have a 10 now in my adjacency matrix?
Well, like in practice, pretty much any graph neural network, you could just like, it can learn to divide by 10 and just do graph convolution on the binary adjacency matrix. But if you like in practice, we often take max here as our pooling method. So if you think max of all the adjacencies, you just really get the original adjacency for most policies, right? Because max, you're just going to get a 1 where there's an edge in the original graph. Yeah. So in practice, you could think of this as just message passing on the original graph for many of our policies.
I have some concerns regarding that sum. Like basically, if you take the sum of all the adjacency matrices for the drop edge, like now let's focus on you're taking all the possibilities of edge dropped, then it's simply going to be like n-1 times the original adjacency matrix, right?
Yeah.
And if you take with the drop nodes, then the sum of the adjacency will simply be equal to, like I don't have the exact thing in my head, but like it would be some form of degree to power something times the adjacency matrix, right? Or like
it would also be a constant times the adjacency.
Well, I don't think it would be a constant because now when you drop when you drop a node, then the node with the most edges will drop more values of the adjacency matrix, right? Like there would be more elements that are dropped when a node has a higher degree. So it seems more like some form of like a constant times a degree power something times the adjacency, or like so.
But if you view it as the edge, like each edge is only dropped twice in the whole bag. Otherwise, it's there. So it's really n-2a, right?
Because basically the two nodes at the endpoints will drop the edge once each.
Mm-hmm.
You drop the edges once each. I don't
for each of the nodes at the endpoint of an edge, right? So an edge connects in graphs, an edge connects to nodes, right? So
oh yeah, no, that's true. Okay, so it's also going to be just like a constant times the adjacency matrix.
Yeah.
Yeah, and so what's the point of doing the sum here if it's just in both cases it's a constant times the adjacency matrix?
Well, in general, it could be a little different for other subgraph policies, but yeah, for node and edge.
What kind of policies?
Like if you think of like maybe you take subtrees or something, it might get kind of wild. Also, if you do sum on egonets, it's a little different. Like I think the edges in like densely connected regions will have higher weight. Yeah, I think that's true for egonets.
And won't that cause a blowout of the values if you have like a large graph using just the adjacency matrix, the sum of the adjacency matrices without some kind of normalizing factor? So without dividing, for example, by the number of nodes or the number of like divided by m, for example, maybe you could have something like 1 divided by m. So if you don't have that term, then and you have a graph with where you do 1000 transformation, then this can really blow up the signal, and this part becomes much greater than this other part here.
Yeah, I think so. So this is like for theoretical reasons, some pooling is the strongest, but Beatrice, is it right that we only do like mean and max for this pooling?
We do max, right? We consider the adjacency matrix of the original graph.
And then for node features, do we do mean? The summing of a node? Yeah.
Oh, right. So I see this is like not a multiplication here, it's a comma, so it can be like any kind of function there.
Yeah. So up to like a different weight initialization of your GNN, it's all equivalent really. kind of.
I think one way to look at this equation here is more like the idea behind rather than the technical implementation of it. So the idea is simply that you have two basically MPNNs working in parallel. One works on the specific subgraph, and the other one works on the aggregation of subgraphs. And this is something that is suggested by another paper that that's where we borrowed the name from DSS. So it's deep sets on symmetric elements. So the idea is that this is the right form to model this kind of symmetries in a maximally powerful way when you use linear layers. So that's why it's not like an equation we made up ourselves. This is just maybe important to remark this. And then in practice, you can play a little bit with this with a grain of salt, but yeah. So the idea is that you have these two MPNNs working in parallel, and then we will sum up the representations, and we keep doing this basically throughout.
Yeah.
Okay. Thank you a lot for the explanation.
Mm-hmm. And yeah, so I put the name of that paper in chat. It's by Hagai and his co-authors. It's a really good paper at ICML 2020. It was one of the best paper awards, in fact. So you guys should check it out. But the interesting part of that paper is that they do a principal in-depth analysis of equivariance, and they see that a lot of works in say computer vision, they do this Siamese networks, like basically deep sets GNN, right? And algebraically, so look at this main idea down here. Algebraically, DSGNN is equivariant to a larger group. What this means is it has more constraints. So in principle, it may be a lot weaker, or I'll just say weaker. Whereas DSS, it preserves node alignment. So we're actually equivariant to a smaller group. So we have less constraints. This group is the one we described in the previous slide about 15 minutes ago. And it really requires node alignment, because when you sum these adjacency matrices, right, you have to sum row 1 of one subgraph of row 1 of the other. So this node alignment is really important for that sum to make any kind of sense, right?
So like the DSGNN does not need this node alignment, because in the end we just end up with an invariant or permutation invariant feature and pool the invariant features with some deep set thingy over all of the different graphs.
Yeah, precisely.
Okay.
Each of these MPNNs outputs a vector, a permutation invariant vector. Yeah.
And obviously these all share the same weights. So this is why sometimes we call it Siamese architecture.
Yeah. Okay. So with that, we're going to move on to the expressive tower of our model. So take it over, Fabrizio.
Yep. So we wanted to characterize the expressive power of this architecture. So we took actually a little detour, and we said, okay, let's try to design what would be the combinatorial algorithmic counterpart of this idea. So let's try to kind of extend the standard WL algorithm to this new framework of working with bugs of subgraphs. And so, yeah, we designed this algorithm. The idea is you start from a graph, you obtain a bag, and then on each of these subgraphs, you, if you remember the update rule we described before, you do a similar update rule for colors on each subgraph. We have additional input parameters to account for this idea of alignment that Derek explained. So if you take a look to the inputs to the hash function this time, we have, again, the current node color on a specific subgraph. In this case, we say it's S. Then we have NVS, which, as before, it's the multiset of colors of neighbors. Just mind that this time the neighborhood is defined on the connectivity of the specific subgraph S. And then we have these two additional inputs. So one is CB, and we call it informally needle color. So the idea is that we basically we gather the colors for the same node across subgraphs. And this is really what we are allowed to do now, just because we have this alignment of nodes. And then finally, the fourth input is basically similar to N, but we call it M. It's basically the multiset of needle colors on the original connectivity, on the regional graph connectivity. So we have this new update refinement rule. Now, at this time, what happens is that we can define a subgraph color, and that this is obtained by hashing the multiset of node colors on each subgraph. And then we can describe a graph, the original graph, as the histogram of subgraph colors, right? And this algorithm actually can, with this general formulation, we can recover another variant. There's the one which actually corresponds is the counterpart of the SWL. We show it in the next slide. And the standard 1WL. So in order to recover the SWL, so a variant where we don't have node alignment, what we need to do is simply to disable the third and the fourth input to the hash function for any policy. And this, interestingly, boils down to having an independent 1WL procedure on each subgraph. So you can imagine we have this bag of subgraphs, and we have 1WL running on each of these subgraphs independently, without sharing any information across them. And then finally, obviously, if we use a trivial policy, like we just create a bug where we only have the original graph, then we recover basically the standard WL or a trivial counterpart of it. Right, so with this little detour, then we managed to show that first, there exist policies such that these two variants are strictly more powerful than 1WL. And the policies for which we approved this were, for example, the ones that Derek showed before. So node deletion, edge deletion, ego policies, and yes, and ego policies. And further, we showed that the neural architecture that we called the SGNN and the SSGNN, so they can implement these two variants, basically. We showed this in particular on families of bounded size graphs. And in the case of DSS, we do require the policies to be edge set preserving. So this means that one edge in the original connectivity has to appear at least once in the bag. And this is obviously satisfied in the case of the policies, for example, node deletion or edge deletion, or even as we always have that an edge appears at least once in the bag. And is needed just because in this way, the connectivity that is induced by the summation of the adjacency matrices recovered the original one, as we were explaining before. And we also showed that we have an upper bound for the expressive power of the SGNN. That is, it cannot be more expressive than the SWL, the second variant. And with these two theorems and the results we have in the literature, then the direct corollary is that our architectures are strictly more powerful than standard MPNNs for these policies, for example. So it means that there are actually pairs of graphs which our architecture can distinguish, but they are not distinguished by standard MPNNs. And yes, let's maybe move to the next slide. Yes, this is Beatrice now taking over.
So we validated the expressiveness claim by considering the RNI and the CSL datasets, which contain graphs that are indistinguishable by 1WL. And we can see in the table the EXP and CEXP datasets, which are the RNI datasets, which contain graphs that represent formulas with the target whether the formula is satisfiable. So in these datasets, there are pairs of graphs that are non-isomorphic, but are indistinguishable by 1WL, and such that only one graph in the pair is actually satisfiable, represent a formula that is actually satisfiable. And we can see from the table that the SGNN and the SSGNN obtain perfect accuracy independently of the base encoder and also independently of the subgraph selection policy chosen. On the contrary, the base encoders that, like we show here, gene and graphcomp, cannot do better than random guessing, which is 50% on exp and 75% on cexp.
Okay, so we went over our method and some tools for analyzing expressive power. And this motivation for our method, if you believe the motivation, which is make bags of subgraphs and then get the right equivariance in your neural network, if you believe the motivation, then our method is like, you know, it's not the most complicated method that satisfies these constraints. But there's still a lot of design choices, right? The subgraph policy, the choice of encoders and such. So we theoretically and empirically analyze these different design choices. For instance, we have our two methods, right? DSS-GNN and DS-GNN. And we could actually prove that DSS-GNN is strictly stronger than DS-GNN for certain policies, as one might expect from our discussion of the equivariance and the symmetries, right? So consider this simple policy, for instance. It is you're supposed to, you take G and you map it to the set of single edges, okay? So each subgraph is like a single edge. And for deep sets GNN, what it sees is just anonymous edges. You know, there's just like, you see 4 nodes and 2 of them have edges between them because it doesn't have node alignment. On the other hand, DSS-GNN, what it sees is this is an edge between 1 and 2. This is an edge between 1 and 3, and so on. Like it knows what nodes the edges are connecting. So what happens is DSS-GNN can just reconstruct the graph. If you just sum the adjacencies of the subgraphs, you get the original graph. But DS-GNN, all it could do is count the number of edges. It can't do like anything else. Because there's no alignment. So obviously there's a lot of graphs where they have the same number of edges, but they are easily distinguishable by say 1 WL, and DSS-GNN works on those graphs. And then for the experiments.
Yeah, empirically, we actually saw this trend in the experiments where we could see that DSS-GNN tended to outperform DS-GNN. And like we show here some numbers to quantify this. DSS-GNN was actually better than the base encoder 91% of the time, while DS-GNN was better than the base encoder 75% of the time. So showcasing the fact that DSS-GNN tended to outperform the DS counterpart.
Mm-hmm. Yeah, so another design choice, the big one, is what subgraph policy to take, right? So to study this, we restrict to the strongly regular graphs. 2 of them are depicted below. These are like very highly symmetric graphs that are very hard cases for graph isomorphism. In fact, some people think that it might be as hard as the general graph isomorphism problem to separate these graphs. It turns out that on this family, we could prove something really strong, which is that node deletion and depth and ego net policies with our DS or DSS-GNN frameworks, these are as strong as 3WL. Actually, they're exactly as strong as 3WL on this family. On the other hand, edge deletion is strictly stronger than all of these. Yeah, so this is like a very nice result that we can't prove in general, but it holds for these strongly regular graphs, which is nice.
Experimentally, we didn't find a strong correlation between the performance of a policy and the application domain, meaning that there isn't a go-to policy to use for each application domain. However, like interestingly, the ego and ego plus policies were found to achieve like excellent results consistently across datasets. And we can see this in the zinc dataset, which contains graphs representing molecules with target the constrained solubility of the molecule. We can see that in the box here, the dsGNN and DSSGNN on the edge deleted and node deleted policies. And we can compare this with the ego and ego plus policies, which were found to obtain better performances with respect to the edge deleted and node deleted correspondings. So the choice of the subgraph selection policy makes a difference in this dataset, and we highlight here the incredible performance that the ego policies can achieve on the zinc datasets.
Yeah, by the way, I think this is a very interesting thing for people to study in the future, and you could check out some other papers that operate on EcoNets. They also often achieve pretty good accuracy. But yeah, so our final kind of design choice that we study is the base encoder, meaning the base graph neural network that we use in these are like dsGNN and DSSGNN layers. So if you replace this message passing neural network in our model with a 3WL strength base encoder, like 3 invariant graph networks, it turns out that we could prove that this also increases the power of DS and DSSGNN. And to prove this, we take our friendly 2 examples of strongly regular graphs here, the Rook graph and the Shrikhande graph. You can see more in our paper. And we show that using an EgoNet policy, 3WL can distinguish these graphs, whereas 1WL cannot in our dsGNN framework. Yeah, we don't actually experiment with 3WL base encoders. I think that's a nice avenue for future work, but we do vary our message passing neural networks that we use, like GCNs, GINs, and GraphCon by Morris. So you can check out our paper for the exact stats on those encoders. And this is the last design choice slide, but I just want to say, like, it's pretty nice that it turned out we could actually theoretically analyze each of these design choices. Like, when's the last time you saw a neural net paper that could do that? And also, it's interesting to check out our experiments, because we show, like, we kind of ablate in many of our tables these different design choices.
Yeah.
Maybe before moving to the experiments, I don't know if there are questions, just to maybe take a quick break.
I'm all good.
Okay. So some general messages about the experiments. So first, I want to remark that I will denote by ESAN the best performing model. So the best subgraph selection choice and best base encoder in this next section. So in our experiment, we found ESAN to generally improve the base encoder accuracy, and we can see this in the table I report here, that is like about the 2 open graph benchmark datasets, MolHIV and MolTox21, which contain graphs representing molecules with target whether the molecule inhibits HIV replication in the case of MolHIV, or the toxicity measurement level in the case of MolTox21. And we can see that ESAN achieves like 2.4% improvement on MolHIV and 3% improvement on MolTox21. And this is just to show the results on these datasets, but it's like a general trend also on other datasets. So we also found ESAN to be competitive with state-of-the-art results. And we can see this in the TU datasets that are shown in the table. There are like here reported 5 bioinformatic datasets from the TU repository and 1 social dataset. And ESAN scores first on 3 of these datasets and obtain very competitive results, very competitive accuracy on the others, with actually small differences with respect to the best performing method. Like then on zinc, we found ESAN to be the best performing model amongst all probably expressive domain agnostic GNN. And we can see that indeed it actually outperforms PNA, DGN, and like these other boxed in violet by a large margin. We also found ESAN to be competitive with provably powerful GNNs, which employ domain-specific structural information. And actually also often outperforming them. And we can see that we actually outperform HIMP and GCN, and like while being very close to the performance of SIN, which is I think like state of the art, and which actually use domain knowledge, right? And I want to remark that all the models here stay in the 100K parameter budget. So the difference in performance really is in the choice of the model, and like because all of them have the same budget. Okay.
Yeah, so maybe a few last slides on the computational complexity.
Or
we're
first,
talking about this.
some
Hannes,
reasoning
sorry?
why you think it helps so much specifically for zinc. Do you have any like intuitions?
Well, I think this is actually a very interesting result that we should try to investigate further. This is somehow what I wanted to convey before. So the idea is that with ego, I mean, this was quite surprising for me as well, to be honest, because with ego policies, which are not for sure, like they're not like specific to molecules. So we don't really inject any information about cycles or rings, this kind of things. We will still be able to be very, very competitive. So yeah, very surprising, very interesting result. And for sure, some of you would like to investigate more. I don't know if Beatrice want to say maybe something about this, but
I think Dominique also has some points.
Yeah, sure. Go ahead.
Oh.
Yeah, thanks. So I think these results are very interesting because zinc is an artificial benchmark where the goal is to count the number of substructure. So it's an artificial task where chemists basically defined a linear model based on the presence of different substructures. So when you look at the results from the SIN here that directly injects the substructure, it's kind of cheating by taking a shortcut towards this specific task, because it's not a real world chemistry task. It's really like a task about finding the substructure. And the fact that the ESAN is so much close to the SIN, it means that it's your hypothesis that it's more expressive, especially in regard to the WL test and in finding substructure. Well, your hypothesis is very right, because the gap between one model that uses the substructure explicitly and one model that doesn't use them explicitly is very small. The only thing here is that we're still with molecules, so we're still with graphs that have that are very sparse and have low complexity in general. But still, like the difference is great, and it would be nice to see the same thing also for denser graphs.
Maybe one additional comment on this is that one thing that is also surprising is that there's really a significant improvement of, sorry, I meant like the ego policies work significantly better than the edge deletion and node deletion policies on this benchmark at least. So they still work very well in general, but the ego policies really allowed us to perform better here, much better. So again, it would be interesting to try to understand this better on this kind of data set in particular. And yeah, and also again, DSS seem to work better than DS, not significantly better, maybe some cases, but as an overall trend, for sure, especially with the ego policy. So DSS worked much better. So I think really lots of things to think about in the future. Shall we move on, or?
Yeah, I would just move on, and like I have a bunch of questions, but I think it's better to have them at the end.
We can also skip this complexity part, maybe, if you want to save some time. I mean, the details are all in the paper if you want, unless as you prefer. We also have some slides on the sampling approach. That was something that it was discussed by Dominique and Derek before. Really up to you, Hannes.
All right, then, yeah, what do you do with the sampling, or what do you choose?
Right, so the idea with sampling was exactly what we were discussing before. So in some cases, you might have bags with too many subgraphs to process. So what do we do in that case? We tried to a simple approach that was to simply uniformly select subgraphs from these bags. So in this case, obviously, we might lose some. We might lose in practice. We might lose equivariance. This is something to be taken into account. But nonetheless, we experimented with this to get an understanding. And what we do at inference, just to also be precise about this, what we do is we perform k-independent samplings, and then we do majority voting in the end. It was interesting to observe that in most of the cases, the performance didn't drop significantly, but Beatrice will show the exact numbers for this. In general, it allows us to obviously run on larger graphs, in the sense that the cardinality of the bug for the policies we have considered, say node deletion, edge deletion, it scales with the size of the graph. So if the graph is very large, of course, the bug will increase in its size. So in this case, this allows us to somehow make this the computational complexity tractable in these situations. And this, as a somehow as a side effect, also we can increase the bar size, and therefore we can also train quickly more quickly in this case. Yep.
Yeah, in the experiment. Oh, sorry.
No, let's have the experiments first.
In the experiment, we saw that sampling did not significantly reduce the accuracy, and in some cases, like it even increased it. And we can see these on these 4 datasets that we report here, and on the DSGNN cases, which we report 2 policies, edge deleted and node deleted. Obviously, the old results are in the paper. And we experimented with sampling ratios 5%, 20%, 50%, and 100%, where 100% means we take the full bag, so no sampling approach is no sampling is done. And we can see that, so first, the performances are very similar for all the sampling ratios. Also, the models tend to outperform the base encoder independently of the sampling ratio. And finally, we can see that for some cases, a smaller ratio was found to even increase the accuracy. And we can see this in the box that we have highlighted as an example. So where we actually have that 5% really improves like the accuracy on mole HIV. Oh, go ahead.
So here, I think it's very interesting to see that using lower sampling improves the accuracy on many different tasks. So like from mole HIV to MolTox21, on the expense, the drop is negligible. So one thing I would like to say on that is maybe the architecture that you proposed, because you're doing the sum on so many different sampling of the same graph, then you're kind of having an over-smoothing of all of these networks. So you have all these networks working in parallel, and then you smooth them all into a single sum aggregation. So I think by using a smaller sampling, maybe what happens is that there's no more, this over-smoothing doesn't happen anymore, and you observe stronger improvement because of that. That's what do you think about that?
So when we do summation, do you think we would incur in over-smoothing in any case, even if we do summation rather than mean over the node features? Because I was thinking maybe with summation, since we also internally we use, I think in most of the cases, for example, gene encoders, right? So my intuition was that not necessarily we might incur in over-smoothing, but I'm happy to discuss this further.
Yeah, the sum is basically just the mean multiplied by the number of nodes. So you will not preserve more information than the mean, except for how many nodes there was in the graph. And gin is known basically to have over-smoothing when you apply it in graph neural networks. So it makes sense here that the sum is also causing some kind of over-smoothing. Yeah, so either like I would suggest either to use a kind of PNA-like aggregation where you use different statistics of what you're aggregating, or you simply keep with the 5% or 20%, which seems to work pretty well in most cases. Like you don't need every possible you don't need every possible augmentations. Like only a few augmentations is enough to increase the expressivity the way you want to do it.
It's interesting you suggested PNA. Why do you think this would help in particular for the over-smoothing issue specifically? Or I wasn't aware of, for example, I wasn't aware of PNA being less sensitive to over-smoothing with respect to gene. But it's interesting also.
So with PNA, you preserve a larger part of the signal, like like here, I'm just suggesting something like that, but you can use a different type of strategies. But what we proved in the PNA paper is that using a single aggregation strategy, then you necessarily lose a lot of the information signal unless you significantly increase the number of parameters. So like you, for the sum to really be injective and preserve all the information, you first need to project your feature vector into a much larger feature vector, then do the sum.
Okay,
which
I understand
will
what you
require
mean
lots
now.
of parameters. Yeah. With PNA, the idea is just that with a few statistics, you can preserve a larger fraction of the information. And you just need to increase, maybe if you use 4 aggregators, then you need to increase 4 times the size of the vector instead of having to increase it like 20 times or 100 times if you have large graphs. So that's the whole idea. But personally, like I don't think that's necessary. Personally, I think that only with 5 or 10 or 20% of the possible augmentations, it's enough to give the expressive boost that you want to give with your method. I don't think like you need fancier aggregation.
Yeah, the only drawback of this is that obviously you might lose permutation equivariance, but it will be interesting to see to what extent you do. So in some case, maybe we can talk also about an approximate equivariance, and maybe you can just make do in any case. And this is what we observed, for example, in these expressive power benchmarks. So even with 20% of the subgraphs, we're still able to obtain 100% accuracy, for example, on Exp. So this means that we are still able to perfectly identify the isomorphism classes to some extent. So yeah, definitely something to take a look at as well, I believe. I can see there are some questions in the chat, but I think Derek is taking care of that. So I don't know, Hannes, you want us to keep going or?
No, well,
So we should take the question from Lucas.
Lucas,
He studied the sampling. Yeah.
Oh, it's not so much a question. I wanted to give a +1 to Dominique's hypothesis. I think I find it very valid. So I was working on this drop GNN paper, and the observation there was usually you drop some things, and most of the time what you drop is useless, but you want to find a few times when what you dropped is useful.
Yep.
And I remember in some intermediate experiments, I think we had mean and nothing worked. And then at some point you print the things and then you're like, okay, it's basically the same. Of course it doesn't work. And kind of the important part is that you somehow are able to see the outliers as outliers and that they don't get noised away by the proper things. So kind of with this thing, I think it flips from the noise and the outlier. Kind of the normal thing is your noise and the outliers are the thing you are looking for. And I think there it's a bit dissimilar to, I think at some point we talked about drop edge, where it's a bit more the other way around, that you actually want to regularize the outliers away. And here we want the outliers.
That's a very nice observation. Yeah. Yeah.
I was also thinking in your architecture, we do this sum or this aggregation, for example, but now if you have some fixed number K of changes that you're looking at, and the number of subgraph does not depend on the size of the graph, then yeah, we could also do something like processing all of the graphs with their own adjacency matrix, right? And then like concatenating the features and feeding them to, and having our information sharing done like that. Like instead of summing all of the different adjacency matrices, we use all of the different adjacency matrices in an MPNN or in a single MPNN layer. And then we concatenate all of those features and feed them through some, or they make up, after some down projection, they make up our next layer of features. And that way,
yeah,
like we wouldn't have
the only problem I see with this is that you are kind of sensitive to the order of the subgraphs, right? If you concatenate.
Oh yeah,
features.
that's a problem. But then you could do some deep set stuff.
Well, deep sets at the end of the day, what it does is it sums, right? And this is what we're doing. Well, maybe
yeah, but
like
you're still using different adjacency matrices to produce the thing that you're summing.
I didn't get this. So what
like
do you mean
for
exactly?
example, if we use the max as aggregation, then it's can very often happen that the max of all of the adjacency matrices is just the original adjacency matrix, and we end up with something, it's just the same as if we were just using our MPNN on ours, or like our standard MPNN. And now if instead we take the different adjacency matrices and we produce some representations from them, some node representations, and then we take the max over all of those node representations, then yeah, we would use all of the different adjacency matrices, right?
To me, what you described really seems like the DSGNN model we have. Maybe just not with all possible adjacencies, but with a few of them, we kind of use them independently, and then we obtain right representations for each of them, and then we aggregate those.
Yeah, but we aggregate them in each layer, right? That's not done. Is it done by DS?
No, it's with DSS. You're right. Okay. If you want to aggregate them at each layer, yes. Yeah, it seems like a special case of DSS, right? Where you are basically changing a bit the second MPNN part. So I think you don't actually, what you're suggesting is you don't do message passing on the original graph, right?
Yeah.
Yeah. So you would only simply do this, what we call needle operation. So you aggregate the representation of a node across subgraphs, but you don't do message passing on the original graph, if I understand correctly.
Well, you also do message passing on the original. Can we maybe go to your slide where you have the formula of your network, like the equation 1? Yeah, or here it's equation 3. Like the second part, or in your paper you write it as L2. In the second part, instead of summing, we take the sum outside of the message passing neural network, basically.
You mean the summation or the sum of the two parts? Sorry, it's really hard to follow this way. Maybe if you can enlighten the, unless Derek or Beatrice, maybe I just.
I can do the drawing thing. we take this sum right here outside. And we do a message passing with all of these different adjacency matrices. And we end up with a bunch of different representations, and then we sum them up. And that way we used all of the different adjacencies and did all of the different message passing.
This is weaker in for like the that single edge policy.
Weaker for the single edge policy. So
because
if we're doing node edge deletions, it's weaker.
No, I mean like that trivial one, I think, right? Is that true? Actually, I'm not sure if that's true. I might be wrong. But yeah, what was your point there? Let's go back.
Yeah, I was just thinking this, to me, just intuitively, it makes more sense because that way we don't end up with this situation, or yeah, it just feels kind of strange to sum all of the adjacency matrices, and yeah, it does not sound very meaningful to have the summed adjacency matrix, or especially if we take the max and maybe just end up with the same adjacency matrix as in the beginning. To me, it sounds like more sensible. Or if we make this argument that if we look at multiple sub connectivities, then we're more powerful. Well, then let's just use the multiple sub connectivities in our message passing instead of this summed connectivity matrix. Yeah, and we just use all of the different connectivities for message passing. I mean, then it's much more expensive, right? Because we have to run many MPNNs, but then we just sum them up afterwards.
Oh, wait, I feel like the outer summation might be equivalent to this, because in the next layer you're summing you're summing these guys anyway, right?
Yeah.
But we're always summing different stuff in the message aggregation. Like if you have two different, yeah, we can just see that it's not the same if we look at this scenario where the adjacency matrix is the same as the original adjacency matrix, right? This can happen where this adjacency matrix is the same as the original one, and then it would not be the same, right? Because we would get different results if we use the different adjacency matrices, and we know that we're able to distinguish some cases where we have the different adjacency matrices.
I meant in like the function approximation sense. But okay, yeah, let's see.
Yeah, okay.
Like there's weights. I mean, like I thought there might be weights in which they're equivalent, but maybe not. Yeah, I don't know.
Let me because here there's something like I'm not sure I understand. Like here you use AI and XI. Isn't that like? And you're not, and here you're using Li also. So here I thought it was implicit that you're summing over all the adjacency matrices, or am I getting this wrong? And you only, well, what's AI and Xi then?
That's the original adjacency, right?
No,
Why is there an index I?
This is subgraph.
Yeah.
I feel like, yeah, I really feel like the outer sum is weaker than our method, theoretically.
No, I'm pretty sure the outer sum is more powerful. It's basically like similar to this discussion that we had about like something like Jin, where you first use the MPNN kind of gives you a neural network before you do the sum. So this becomes kind of the injective function on which you later do the sum. Whether if you do the sum in here, you don't have this notion of injective function that allowed Jin to be powerful.
Your previous layer can just be the injective function.
Yeah,
like,
I mean xj is the output of the.
You have to think of this as like multiple layers, right?
So well, so maybe the problem probably is like we brought x, but we meant like the representation of the other previous layer. It's not the original input features. So in this case, xj that we have in the internal summation is the result of the L layer on subgraph J at the previous layer.
Okay, yeah, but we can see the situation where this is A. This is just, oh, whoops, no. Yeah, okay, like I now get what you mean, because we always have the different subgraphs here, right? And we're aggregating the features of the different subgraphs here. So we always have the thing that I said, we always have that in the next layer anyways.
Yeah, I think so, yeah.
Okay, so let me understand something more accurately. What do you do with all the i's here? Like, do you concatenate all of this thing for the different i's? Like, what's going on? Do you concatenate them, sum them?
We sum them.
This is just a layer, right? So we keep all the i's through the whole architecture, and then in the end we do the readout. But at each layer we keep them all, so it's you can see it as a tensor, right?
Okay, so at the end of all the layers, you do the aggregation. So in some sense, it's kind of if the sum is already outside. It's kind of if you have a model with one layer, it would be the sum is already here. So you have what Hannes is trying to do, like supposing a one network architecture.
Yeah. Yeah, I would say so, yeah.
Yeah.
For one layer, yeah.
Okay. I was thinking that the sum was done at every layer, but it's not. But it makes sense that to do it only at the end. Yeah.
Well, but we kind of are doing the sum at every layer, because at every layer you have the different adjacency. And then here you are summing the features that come from the different adjacency in the previous layer.
So this form of summation, yes, but at each layer, each subgraph, so the features on each subgraphs will be different, will be specific to that subgraph.
Yeah.
Yeah, okay. So because I had the impression Dominique was suggesting that would somehow summarize them all. But no, like they're kept specific for each subgraph throughout the whole architecture. That's why I was saying you could imagine it as a X instead of a matrix, as a tensor, where we have an additional dimension, which is the dimension of subgraphs.
Yeah. So to go back to Hannes' point here, I think putting the sum here would be more powerful, but it would be also much more expensive to do that. And then if the idea is just to get a quick summary, so this could be viewed like as just a quick summary of what's happening across all the different subgraphs. So you don't necessarily need it to be too powerful, because then maybe there's too much knowledge that gets shared.
It's not more powerful, because you're doing this anyways.
Yeah, I think it's definitely less powerful. Like, yeah. Yeah, and like you're doing every operation you could do in the next layer if you, instead of putting the sum outside. Yeah.
Instead of putting the sum outside, you have the sum here basically in the next layer. Okay. Good discussion. Let's I don't know, get to more questions, or do we still want to go on with some slides?
Maybe Derek, just take the slide on the comparison.
What? Oh, password?
Yeah.
Oh yeah, so it's very important to note that many other methods in the last several months, there's been some similar methods that have been proposed with differing motivations. Like there's this reconstruction GNN by Cotta et al. It's very similar to our DS-GNN with node deletion policy. Like they take the node deletions, they put them through Siamese networks. They also do sampling and deterministic versions. Drop GNN is mostly the sampling, but it's also a node deletion policy. And there's this GNN AK, which is very similar to our DSS GNN with the EgoNet policy. And something nice is that these things have kind of different motivations and whatnot, like reconstruction conjecture, or like thinking of like filters in a convolution. Whereas our ESAN framework kind of unifies and generalizes all of these methods with like really two main ideas, which is bags of subgraphs and the required equivariance. Yeah.
Well, I think maybe just let's make the point. Right. So the idea was at the beginning to decompose a graph into a set of subgraphs. This gives us a bag. The bag is an object per se with a certain symmetry, and we study the symmetry, and we want to process the bag respecting the symmetry, right? And this is what led us to define this architecture we discussed. Experimentally, we observed that this framework, in most of the cases, allow us to outperform the base encoder that we would use, which in our experiments was a simple MPNN. It was in general competitive in performance with other models, and in some cases we observed also surprising results. For example, in the case of zinc, right? So without injecting specific domain relevant information, we were able still to get very competitive performance. The model enjoys probable expressiveness. We have native equivariance, with the caveat that we might lose it in the case, to some extent, in the case where we do subsampling. And we are generally domain agnostic, as we were saying. In terms of future directions, yes, many of them we already emerged from our discussion. Maybe we might like to consider other policies, maybe to see if we can study additional structure on bags. So instead of considering bags as simply as sets, maybe you could consider them as more structured objects. Maybe we can consider them as graphs. And then, yeah, as I was saying, stochastic policies may tamper with the equivariance of our approach, but to some extent, we observed that in practice, this wasn't a problem. So it might be interesting to also study this through the lenses of approximate equivariance and many other things. Yeah, so thanks for being here, and thanks for the interesting discussion. I think we're happy to say if there are other questions.
Yeah, well, thank you for bearing with our criticisms and our skeptical questions, and for the awesome presentation and for the awesome paper itself. Then, no, I'm gonna go with my question first, Lucas. So you have this, yeah, you present in your paper basically these three different approaches or three different directions of aligning to the KWL hierarchy, augmenting node features with exogenous identifiers, or leveraging on structural information that cannot provably be captured by the WL test, like as ways to improve the expressive power. Sorry, Lucas. Which way, or which of these three do you see as the future, so to say? Or which do you like the most?
Bottom one. It works on sparse graphs, efficient on sparse graphs. It's flexible. It has a nice new theoretical framework, counting substructures, really started by the people at NYU.
Wait, if you say bottom one, let me repeat, that's leveraging structural information. So like, yeah, okay, you have the correct slide. Never mind, sorry.
No, sorry, I was excited. Okay, any other thoughts? Also, so the theoretical framework of counting substructures is much more fine-grained than what we have for graph isomorphism, because like 1 WL to 3 WL is a huge jump, but like being able to do rings, like count rings of certain lengths, is like more interpretable and much smaller of a jump. And yeah, spectral information, yeah. You want to chip in, Dominique?
I actually think the spectral information is super nice and sounds very intriguing, but I'm not a fan. But we have a fan here.
In general, I think this whole idea of working with positional encodings, we haven't talked about this in specifics, but it's also it's interesting, and so it may also get close to this directions, right? So in a sense, using positional encodings or somehow encodings, additional encodings on nodes, so this can give us a form of identifiers. And this was the initial idea that we had in the GSN paper, which here is categorized as substructure aware message passing. But to be completely true, it's also a little bit on the second bullet. So it's also a bit about identifiers. I think one of the main motivations at the beginning when I was working with Yorgos was we would like to have identifiers, but at the same time something that would have some important domain information, not just something random, or because at the end of the day, you also want to generalize. And if you use random identifiers, this might be a problem. So this led us to pick substructures. So therefore then it became like a substructure aware message passing model, but the motivation was around identifiers. And I think in general, positional encodings would be, it's a nice new research direction in the GNN community. I think maybe somehow close to this ideas we discussed in terms of adding augmenting nodes with the exogenous information that cannot be directly captured by GNNs.
Okay, then I want to say sorry to Lucas, and let's go with your question.
Worries. Again, it's not a question. Some idea I had for the last slide when you talk about other policies. I think what could be interesting, I think the perturbations you do are very careful, but maybe you can try something more aggressive. And for example, or maybe it's not even more aggressive when you do a 3-layer GNN and one node is here and this node is 7 hops away. You know you can do stuff with both of them and it's the same because they never see each other because you only do 3 hops. So maybe you can compress several of your candidates into one candidate actually, and then everything might get a bit more efficient and effective.
Yeah, so in general, I would say yes. So it's related to the previous point you made, right? So we might not know in advance, like many, maybe we have a lot of redundant information that we wouldn't care anyway. And it's all about picking some of these candidates. And this is something. So now maybe you're suggesting something different, which is instead of removing just one thing at a time, let's just be more. So for example, you remove subgraphs, entire subgraphs, or a set of edges. Is this what you're proposing? So we are more aggressive on the connectivity that is left after we.
I tried to make an extreme example. So you have a click here, and then you have a chain of 10 nodes, and a click here. And then you will try every one of these independently. But for this graph, you will never you do 20 times the same thing, because this chain is far larger than your number of layers, aka your receptive field. So, I mean, in this example, you could do something on the same clicks, but in general, there might be, you can roughly check that things don't overlap in terms of receptive fields and throw something in every component, and then you get some speed up, especially for molecules. I mean, often for molecules, it's not so bad as for Cora, where you do 2 layers. But when you don't have that many layers and the things are sparse, you can do many things at the same time.
Oh, okay. That's very interesting. So for instance, for node deleted graphs, I think, if you have 2 automorphic nodes, then they have the same node deleted subgraph, right? So you could just take one of those. So that is pretty interesting.
And yeah, I mean, also this would help you when things get larger or the graphs get larger.
Yeah.
Most of the nodes, for many nodes, it doesn't care if the remaining graph is 10K or 100K or 200K or whatever many nodes, because it's never in your receptive field. So
yeah, I understand.
That was some nice thing that Andras found in the drop gen, and that the thing, kind of how you drop is not dependent on the graph, but on your receptive field, or what you consider by sharp looking or gut feeling or grid search or whatever to be a good receptive field size. And the drop probability is only dependent on that. And if the remaining graph is 10 billion, for this node, it doesn't matter. And
right.
I think in generally this assumption or this line of thinking holds much better for the molecules, because there it's almost a regular graph. I mean, yes, sure, some nodes have 5 edges and maybe others have 2 or 1. But in general, the degrees are all very similar. I think this all goes, or it goes very bad once you go to a social graph and you have Lady Gaga in the center of the graph with 10 billion followers. And then for this node, everything goes bad.
Yeah, I mean, Lady Gaga would basically break any possible GNN anyway, but no, I understand. Yeah, you're making a good point. So in a sense, is the coupling the computation on specific graphs with respect to certain subgraphs. So yeah, I understand. It's a very good point, actually.
Thanks, and also thanks for the presentation.
Thanks to you for chipping in with these interesting observations.
Thank you a lot for the great presentation. It's the first time we have a trio of authors, I think, to present the papers simultaneously. And it was quite fun to have like the presenter change. But it went smoothly, so that's impressive. And I really like the work and enjoy the work. And as pointed out by Lucas, I think like having some other forms of random dropping, of non-random dropping, but like more guided droppings could be a good next step. Mm-hmm. And since I'm a fan of spectral graph theory, then my suggestion is just to take try having an eigenvector-based form of random sampling. Well, that's just a simple suggestion, but I think what you've done in the work with all your different suggestions and showing the empirical results of the different kind of drops, I think it's very impressive, and I really enjoyed reading your paper.
What drop did you think in the beginning would work the best, or what augmentation? Did you expect the ego networks to be the best?
Beatrice, you want to take this?
No, I think we didn't expect the EgoNet to be so best performing and consistently. Actually, we kind of tried to explain the performance afterwards, but yeah, it was surprising for us as well. And which sampling approach we expected to be the best? I think like no sampling, but in reality, we found out like different. Ratios to perform like very well. So
like I intuitively like the edge dropping the best because of your figure 1, where you have this nice example of the graphs that we can't distinguish, and then we move some edges, and then we can distinguish them, or we can distinguish them based on their backs. Yeah.
Well, those two graphs can also be distinguished by node dropping.
Yeah, by node dropping, but it's just your nice explanation, and the ego networks just they're not as intuitive to me. Mm. All right, but then let's call it a day, I guess. Definitely many interesting directions this line of work could go in, and we will find out if positional encodings or encoding substructures in some way will be the future for more expressive GNNs. And if you want to join our reading group sessions yourselves, you will find links in the description, where you also have all of our social medias, and you can join our Slack or our mailing list to get weekly updates on what paper is next.